Good morning, everyone. I'm Jialin Chen from National Cheng Kung University, and the host, Professor Huang, is having another meeting right now. So I'm hosting this talk, and today it's our honor to invite Professor Wei-Po Huang to share with us about the comprehensive coastal hazard analysis and risk governance for the small natural islands around Taiwan. And Professor Wei-Po Huang has many experience about coastal hazard modeling and analysis. And he previously worked in many projects related to the coastal hazard management. So today, we are happy to invite him to share with us his experience. And so let's welcome Professor Wei-Po Huang. And I will pass the microphone to him.
Okay, thank you, Professor Chen. I will share my slide. Okay, greetings, whether it's morning, afternoon, or evening in your part of the world. I'm Wei-Po Huang, come from National Taiwan Ocean University, and extend my gratitude for joining us at the AOGS online seminars. It's a privilege to be welcomed by AOGS to delve into the topic of coast risk analysis and management for the small natural islands surrounding Taiwan. In today's session, we'll focus on the outcomes of several government commission projects, emphasizing their feasibility and practical applications. Our aim is not only present these findings, but also to share our experiences in implementing effective adaptation strategies. Allow me to take a moment to introduce myself. Following the attainment of my PhD degree, I spent 9 years in engineering consultancy. This period of engagement with engineering consulting firms provided me with invaluable experience in addressing real-world challenges, bridging the gap between theoretical research and practical application. My research interests are centered around coastal hazard risk assessment and management, coastal morphology assessment, and coastal environment investigation. Your feedback and potential collaboration are eagerly anticipated as we work together to minimize the impact of coastal hazards on these natural islands. Today's presentation will unfold in 4 distinct parts, each contributing to a comprehensive understanding of our subject. We will commence with a background introduction, providing the context and setting the stage of our exploration. Following that, we will delve into an examination of the coastal environment within the study areas, offering insights into the small natural islands surrounding Taiwan under consideration. The third segment will focus on elucidating the methodology employed in our risk assessment and the analytical framework. Finally, we will unveil and discuss the results, drawing the conclusions from the data and observations gathered. Let's begin by delving into the background of coastal hazard management. This framework is rooted in international initiatives such as Agenda 21, the Rio Declaration on Environment and Development, and the Statement of Principles for the Sustainable Management of Forests. These documents advocate for the adoption and implementation of integrated coastal zone management, ICZM, tailored to local conditions by coastal nations. ICZM comprises 5 essential components as illustrated on the slide to successfully attain our subjects. It's crucial not narrow our focus to individual project alone. Instead, we must concurrently consider and address the interactions among the various projects. This holistic approach ensures a more comprehensive and effective strategy for managing coastal hazards and promoting sustainable coastal development. Our project aligns close with the objectives outlined in Sustainable Development Goals, SDGs, item 9, 11, and 13. SDG item 9 focus on industry, innovation, and infrastructure, while SDG item 11 emphasizes sustainable cities and communities. Additionally, SDG item 13 targets climate action. Specifically, our efforts are geared towards enhancing the resilience of the social environment in response to the threats posed by climate change. By addressing these interconnected goals, our project aims to contribute to the broader agenda of creating robust, climate-resilient social environments. Through strategic initiatives and risk management measures, we are actively working towards fostering sustainability and adaptability in the face of climate-related challenges, in line with the global aspirations of sustainable development goals. Here, let us discuss the legislative framework in Taiwan. Significant strides have been made in coast management with the implementation of Coastal Management Act in 2015 and the subsequent enforcement of the Integrated Coast Zone Management Plan, ICZMP, in 2017. These legislative frameworks are designed to proactively address coast hazards, emphasizing the importance of coast management practices. The ICZMP specifically designates first and second grade coastal protection zones on the main island of Taiwan. These zones are determined based on the severity levels of various coast hazards, including storm surge, coastal erosion, flooding, and ground subsidence. Because of socioeconomic status is not considered in the designation, it is not easy to formulate strategies to cope with it. Risk assessment for coastal areas constitutes a scientific process aimed at comprehending the vulnerability and hazard associated with coastal regions. The outcomes may play a pivotal role in identifying priorities for resource allocation. By systematically evaluating the risk posed by different coast hazards, we can strategically allocate resources to areas in greatest need, thus enhancing our overall resilience and preparedness in face of potential threats. In terms of risk assessment, the Sendai framework for disaster risk reduction emphasizes a people-centered approach and outlines 4 priorities for action. Firstly, understanding disaster risk. Secondly, strengthening governance. Thirdly, investing in hazard risk reduction for resilience. Fourthly, enhancing disaster preparedness. Efficient coastal management can be effectively linked to this hierarchical structure by leveraging quantified values derived from risk assessment. This approach ensures that coastal management strategies are informed by a comprehensive understanding of specific risks in a given area. A question is being raised here. The ICZMP designated first and second grade coastal protection zones in Taiwan. However, why is it necessary to conduct additional risk assessment for small islands? This is because the ICZMP designates first and second grade coastal protection zones primarily based on the severity of hazards, with less emphasis on societal aspects. Additionally, the designated spatial scale in coastal cells may not be suitable for small natural islands. In this research, we will address the following two issues. Issue one, prioritizing countermeasures for smaller islands without designated protection grades, but with the outcome of the risk assessment. Issue two, overcoming constraints and implementing risk management. The constraint conditions for small islands include the small islands have limited survey data and they are more vulnerable to unknown risks exposed to the impacts of climate change, unless they were in the phase of incomplete infrastructure development. To compensate for the insufficient data, satellite imagery and numerical simulation techniques are suggested. This allows for a more thorough understanding of potential hazards and aids in the development of effective strategies for coastal management and mitigation. Combining satellite imagery with numerical simulations enhances our ability to comprehensively assess and address coast hazard threats. Obviously, the implementation of comprehensive risk assessment and management can be conducted based on this information, encompassing hazard analysis, human societal vulnerability analysis, and resilience enhancement, unless the risk treatment. Next, let's explore the environmental characteristics of study areas. We will concentrate on three islands, namely Kinmen, Green Island, and Oki Island today. Let's begin with Kinmen. Kinmen Island is situated off the southeastern coast of China within Taiwan's maritime domain, carries a rich historical tapestry shaped by its strategic location. Positioned at the crossroads of the cultural influences, Kinmen has evolved over time, showcasing a resilient spirit that has allowed it to transition from a military stronghold to a beacon of cultural heritage and natural beauty. The headlands surrounding the coast are predominantly composed of granitic gneiss, characterized by layer hardness and resistant to erosion. In contrast, the bays nested between these headlands are composed of sand or mud, shaped by a combination of natural process and human activities. This unique geological composition adds to the island's diverse and captivating landscape. Green Island and Oki Island are situated as small volcanic islands in the Pacific Ocean of the eastern coast of Taiwan, both captivating coral reefs in their nearshore regions. Renowned for their natural beauty, these islands have become popular tourist hotspots, attracting visitors with their stunning landscapes and vibrant marine environments. The local reefs are distributed around the islands and the coastal morphology remains relatively stable. In Kinmen, most land use within the coast areas is designated for forests. The built-up town is situated in the southwest corner of the island, indicating a concentrated urban development in that specific region. Regarding Green Island and Oki Island, the majority of the residents are indigenous people, owing the prevalence of rugged rocky hill in the island's central region. The majority of residents are compelled to reside along the coast within the confined plains. As evident from the three islands, the development of the hinterland along the coast was limited. However, due to recreational needs, the designation of the conservation area, large-scale hard engineering measures to prevent coast hazards are prohibited. Adaptation measures are suggested. In terms of hazards, Kinmen Island faces the challenge of coastal erosion. The situation is further exacerbated by the detection of illicitly operated Chinese boats engaging in the sea sand dredging near outlying region. This unauthorized activity contributes to the ongoing issue of chronic coastal erosion, posing a threat to stability on the island's coast areas. Turning to Green Island and Oki Island, both are regularly subjected 3 or 4 typhoon invasions each year. As the typhoon approaches, powerful winds combined with ocean waves pose a significant threat to the coastal hinterland, potentially causing considerable devastation. However, for a comprehensive understanding of this hazard and effective management, there is a need for quantifying the risks. Detailed investigations and further analysis are imperative to undertaken through a thorough and precise assessment of potential impacts. Drawing upon the legal framework and the specific needs of the small islands, we propose the following works to effectively mitigate coast hazards and promote sustainable use. Initially, evaluating coast erosion necessitates a critical examination of shoreline change trends, a task that proved challenging for islands lacking bathymetric data requires for such analysis. In light of this constraint, satellite imagery emerges as a valuable alternative, offering affordability and access to abundant historical information. However, a notable drawback is its limitation in facilitating volumetric bathymetric change analysis, posing a challenge in obtaining a comprehensive understanding of coastal changes. Furthermore, it's crucial to acknowledge that shoreline obtained from satellite images are influenced by tidal elevation, and for the sake of systematic comparison should be adjusted to 0-meter isobase. This modification ensures a consistent baseline for evaluating and analyzing shoreline changes. The slide presents an overview of various satellite images, detailing their characteristics such as resolution and monitoring period. Specifically, we opted for images with a clear view within the last 5 years. To establish accurate coastlines, we employed the COSAT software. Subsequently, these coastlines are underwent modifications, accounting for tidal elevation and bathymetry slope adjustments to establish the 0-meter isobase for more precise analysis. In addition to satellite images, images obtained from unmanned aerial vehicles, UAV, were also utilized. UAV for routine survey applications at the coast have come of age and are no longer the latest thing, more suited to the specialist researcher or amateur enthusiast. Off-the-shelf survey-grade UAV equipment, data processing, and analysis tools are now readily available to practicing coastal engineers, managers, and researchers. UAV provide an efficient and cost-effective survey tool for topographic mapping and measurements in the coast zone. Structure from motion with multi-view stereo techniques produces fine resolution and spatially continuous 3-dimensional topographic data. The wave climate encircling the islands exhibit variations since 2 sides are sheltered by China, while the remaining sides faces the open sea. Limited by a single long-term monitoring buoy, the available data cannot capture the diverse wave climate comprehensively. To address this gap, a numerical simulation study covering the entire region was conducted. To validate the accuracy of the simulation, short-term acoustic Doppler profiler, ADP, measurements were utilized for parameter calibration. These short-term measurements conducted using ADP allow for derivation of wave and current climates. Additionally, correlations between the short-term and long-term data were established, ensuring the reliability of the simulation results. Two Mach 21 modules from the DHI were used to study the effects of wave and current forces. The spectral wave SW module derived from the conservation equation for the spectral wave action density was used for wave fields. Simulations of current fields were done using the hydrodynamic HD module, which is based on solving the incompressible Reynolds average Navier-Stokes equations. The study area was divided into offshore and nearshore regions to comprehensively investigate the impact of typhoon waves and surges on the coastal areas. Wave and current fields were analyzed in both regions. The simulated wave was employed to examine the distribution of wave heights along the coast, providing insight into the effectiveness of coastal defenses. For current simulation, wave radiation stress and tidal currents were utilized as a kinematic boundary to model the strength of nearshore currents and the inundated areas during typhoons. This approach enables the evaluation of coast hazard mechanism arising from marine forces. Simulations were conducted to model typical typhoon routes that impact the study areas as illustrated on the slide. Essential typhoon-related parameters such as routes, central pressure, etc., were obtained from the Central Weather Administration in Taiwan. The presented slide showcases one of the simulated cases depicting the wave field. The result illustrated the distribution of wave heights and directions, revealing that each location faces distinct risks of wave impact. These simulations provide valuable insights into the potential variation in wave hazards across different locations within the study areas. As mentioned earlier, both the survey data and results of numerical simulation were utilized as factors in the risk assessment. The combinations of potential hazard and vulnerability within coast areas can be used to generate risk maps. In the risk matrix, the hazard component consider the index of nature factors, while the vulnerability component takes into account the index of society, economy, and resilience. In the risk analysis, we undertake a comprehensive approach that involves risk identification, risk classification, risk evaluation, and risk treatment. These steps collectively contribute to the quantification of integrated coast zone vulnerability index. In the initial phase risk identification, we prioritize the identifications of factors that dominate potential risks. To achieve this, we thoroughly examine the characteristics of Taiwan's coast hazard, socioeconomic environment, and the regulatory landscape, creating a comprehensive database of risk and vulnerability factors. Employing the fuzzy Delphi method, FDM, we carefully select representative factors tailored to the unique attributes to the study area. The hazard index comprises 4 key components: coastal environment, coastal line changes, buffer zone, and protective structures. These elements collectively contribute to a nuanced understanding of factors influencing coast hazard. Simultaneously, the vulnerability index incorporates considerations of socioeconomic environment and adaptability. By integrating these aspects, our methodology aims to prove a holistic assessment of both hazard and vulnerability factors, forming a solid foundation for subsequent analysis and the development of effective mitigation strategies. In the second phase, risk classification involves assigning grades to each identified factors using qualitative analysis, quantitative analysis, or semi-quantitative analysis. For instance, a qualitative comparison between a natural coastline and one fortified with concrete breakwater allows for the classification of the latter as having a lower hazard proneness. This process of grading factors enable a more nuanced understanding of varying degrees of risk associated with different elements within the study areas, facilitating a comprehensive risk assessment. In the third phase, the study conducts risk evaluation by utilizing the analytical hierarchy process, AHP, to calculate the weight relationships among representative factors. The AHP was used to organize the basic logic of the system by breaking down the problem into smaller constituent parts, followed by simple pairwise comparisons to development priorities in each hierarchy. This systematic approach enables a structured assessment of the importance and influence of each factor, providing a quantitative foundations to comprehend their contribution to overall risk. Through the application of AHP, the study seeks to establish comprehensive and prioritized understanding the relative significance of identified factors in the context of risk within the study area. Following this assessment, the hazard and vulnerability factors are multiplied in 5 times 5 risk matrix, resulting in 5 distinct classes: high, moderate, low, and low levels, respectively. In the fourth phase, the study focuses on risk treatment, using the established risk classes as a guide for subsequent adaptive strategies based on the estimated risk levels. It is essential to recognize that risk is a combination of hazard and vulnerability. While the overall risk levels may be deemed moderate, the composite hazard and vulnerability components can vary in their respective grades. One scenario may be dominated by hazard, while another may be primarily governed by vulnerability. Therefore, the risk treatment involves strategically reducing the overall risk by addressing either the hazard or vulnerability, depending on their relative contributions to the outcome or to the composite risk level. The target approach ensures that interventions are tailored to specific dynamic of each risk scenario, enhancing the effectiveness of risk mitigation strategies. Finally, let's proceed to share the result and draw conclusions. According to the historical information, the 3 islands were exposed to various types of coastal hazard, including coastal erosion and typhoon surges. The identification of coast hazards, specifically coastal erosion, involves a multi-step process. Initially, the detection of shoreline changes from satellite imagery is performed, and to establish the 0-meter isobase, adjustments are made by using in situ measurements of each of beach slopes and tidal elevations. The change rates of the satellite-derived zero-meter isobase are found to be consistent with those derived from in situ surveys, validating the feasibility of estimating zero-meter isobase from satellite images. Historical satellite images from the period 2018 to 2021 were collected, and the estimated zero-meter base revealed a rescending pattern during summer and an advancement towards sea in winter. This analysis unveiled the trend of historical zero-meter isobase displacement. To address the limitation of satellite images in offering volumetric change data of beach face, structure from motion with multi-view stereo acquired from a UAV-mounted camera is suggested for future monitoring efforts. The presented slide illustrates the volumetric change of the beach face during the winter season of 2023, with the areas of accretion marked in blue and the areas of erosion marked in red. Notably, a large accretion area is observed, aligning with the historical trend in the morphological change. Short-term measurements conducted using acoustic Doppler profiler played a crucial role in calibrating simulated parameters. These measurements were then compared with long-term deep-sea measurements to ensure accuracy and reliability. The study specifically delved into the analysis of wave refraction and diffraction, examining how the propagated wave behave in the situated area. This comprehensive assessment helps refine the simulation parameters and ensures that the simulated wave patterns align closely with the in situ measurements through both short-term and long-term measurements. As depicted on the slide, a long-term measure is situated outside of the bay, represented the open sea marine climate. Conversely, the short-term term measurement is within the bay area, representing the nearshore marine climate. The wave direction can be observed reflecting from the deep sea to the nearshore in measurements. Here are some results of the major marine climate. This dominant wave direction is highly correlated with direction of sediment transportation. The comparison of simulated and measured values serves as a crucial step to validate the appropriateness of simulation program and parameters conducted in the model. As depicted on the slide, the measured data is represented by the black dotted line. In contrast, the simulated data is depicted by the blue dotted line. This comprehensive validation process includes a comparison of wave height, wave period, wave direction, as well as simulated current fields and the variation of tidal elevation. These observed synchronicity between the measured and simulated values, especially during critical events like typhoons, highlights the accuracy and the reliability of the simulation model. This validation enhances confidence in the model's ability and effectively capture the predict marine conditions, affirming its suitability for assessing and understanding dynamic coastal processes. As mentioned earlier, our simulation involves studying typhoon propagating along different routes to access hazard-prone areas. In the case of a typhoon moving from east to west, the waves are vertically incident on the northern shore of Oki Island. One validation case is Typhoon Koinu. In October 2023, during this event, the waves were vertically incident on the breakwater of Kaiyuan Port, significantly impacting the stability of the harbor and the safety of the berthings. This resulted in a substantial disruption, with 80% of ships in Kaiyuan Port capsizing and sinking, and the concrete blocks at the mouth of the port toppling. This validation case underscores the importance of simulating and understanding the potential impact of typhoons on coastal infrastructure for effective hazard mitigation and preparedness. It should be noted that the simulated results of Kinmen were not presented here. They were conducted in the same process to study the impact of typhoon waves on the hinterland. According to the results of the anonymous FDM-based questionnaire, representative hazard and vulnerability factors were selected. Generally speaking, vulnerability can be defined as the characteristics of coastal communities that enable them to respond to and recover from hazards. Verifying representativeness of the selected vulnerability factors is challenging. On the other hand, the process to verify the representativeness of selected hazard factors is feasible. For example, examine the factor of wave height involves in extracting the simulated maximum wave height in front of each coast defense structure within each typhoon and sorting them. The maximum wave height is ranked as 1. The scores of each seawall for each typhoon event were then summed up in bar chart for comparison. A lower total score indicates a greater wave height for the sector, suggesting a high hazard proneness. The 3 pink marked coast defense within renovation and restoration records over the years show consistent results. This proves that representativeness of the selection factor. Above all, this suggests that the assumption that experts can reasonably select hazard factors, and conversely, the vulnerability factor they choose may also be correct. Here are the risk map for Green Island and Oki Island respectively. It is evident that vulnerability plays a predominant role in influencing overall risk. The density of population, economic activities, and building settlements within area 200 meters from the sea contributes a relatively high vulnerability risk. For example, during this year's Typhoon Koinu invasion, Dongji village suffered most severe damage, primarily attributed to the proximity of residents to the coast. The risk treatment can be categorized into 3 strategies, including protection, accommodation, and retreat based on their respective risk level. As protection strategy, the Coastal Protection Authorized Entity, the 8th River Management Branch, shall focus on maintaining the functions of existing protective facilities as a short-term task. In the long term, conducting a feasibility assessment of coastal environment improvement is crucial. Additionally, an assessment of bionic coral reefs and other facilities in collaboration with the authority of aquatic animals and plants is necessary. Reflecting on the past experiences, the disposal of broken or obsolete electric poles with the intention of creating artificial reefs had positive motives. However, insufficient survey and planning led to unintended consequences, causing damage to the indigenous reef and disrupting the underwater ecosystem. This underscores the importance of careful environment assessment and planning in implementing such initiatives to ensure they contribute positively to ecosystem. As an accommodation strategy, the 8th River Management Branch should review and update coastal hazard risk assessment. The local government should maintain the existing land use density and avoid new or expanded areas to development and utilization. At the national level, strengthening the resilience of life support systems, such as electricity, water supply, and communications is necessary. As a retreat strategy, based on the grade of risk assessment not being high, there is currently no need to plan for retreat management. Here is the risk map for the other case, Kinmen Island. After the assessment, the width of the buffer zones and the geophysical property dominate the overall hazard risk. The slide showcases one of the protection countermeasures considering the protection criteria and the landscape. Specifically, the embankment section from the west of Chengong Beach to the east side of Shangyi seawall reveals a visually messy and non-harmonious landscape with the new natural surroundings, primarily attributed to the scattered concrete blocks. It is suggested to relocate the existing concrete blocks in front of the vertical embankment and pave it with rock. This approach aims to create a close to natural environment, enhancing the coastal recreational setting and improving the overall landscape. Finally, here we draw conclusions. Previously, coastal protection resources were located according to hazard damage records and the public petitions on the small islands. With the scientific analysis, the hazard levels and the origins of risk are classified and quantified, thus indicating new priorities for resource allocation. Moreover, the competent authority of coastal risk management is precisely divided and collaborated, which is more resilient to climate change. Thank you for your all listening. Thank you very much. That's the whole speech.
Thank you, Professor Huang.
Yeah.
So if you have any question, the audience, if you have any question, you are welcome to discuss with Professor Huang. Or if you are not convenient to speak, you can also type in the chat box, and I can read it loud for you. Okay, while waiting, I'm interested in the coastal accretion. I think it was based on the numerical result.
Yeah.
Okay, so basically for the two islands, Lanyu and the Green Island, they do not have the coastal erosion problem, but they have kind of shoreline accretion. Is it correct? That's what I read from your slides.
Yeah,
Okay.
because Oki Island and Green Island were surrounded by coral reefs, so they are more the basements were more hard, so they are not suffering the coastal erosion, but they are located in the Pacific Ocean, so they will suffer typhoons invasions 3 or 4 times a year. So during the typhoon, the waves energy will be huge and impact on the coast. That will be most devastate cases to the local residents.
So just curious for the accretion part of the coast, those are coming from the sediment is coming from the sand from other area, maybe from offshore they bring sand during a typhoon period to cause the accretion. So
You mean Kinmen Island?
I don't remember which island, sorry, but I
Oh,
remember one of your simulation you show the blue color, which is accretion.
oh yeah.
Yeah, I just wondering, is it like the sediment source coming from the offshore area? Because in those area there is no riverine input, no huge riverine input, but probably the sand coming from the offshore area cause the accretion.
Okay,
Okay.
I'll find that slide. Yes, this one. This is the location in Kinmen Island. As here
Oh,
you can
okay.
see, the sediment were nested by the nested in the bay. So because Kinmen Island is sheltered by China and Taiwan, so the wave energy is minor in the regular times. So this sediment will not will not by leave the coastal cells. They just transport doing the accretion in winter and erosion in summer, and they are just in the coast cell, not leaving the coast cell.
Oh, okay. So this is the longshore transport phenomena. I
Yeah,
just within the cell. Okay.
yeah,
Mm.
just within the bay, not leaving this bay.
Okay. Yeah. Thank you. And so, any other questions from the
Oh,
audience?
yeah. I have a question. Can I?
Okay.
Please.
Can I have a question?
Yeah, sure.
Sure.
Okay. I'm Huang from China Earthquake Network Center. I noticed that your presentation, the tsunami waves induced by earthquakes is not included in your presentation, right?
Yes, not included.
Okay. No earthquakes occurred in nearby?
Yes, the earthquakes is most happen in the east of Taiwan. However, because the earthquake is not consist in the legal framework, because it's a sudden, it kind of appears in sudden, not a chronic impact to a region. So this is not considered in the legal framework. So we are not put in this factor into consideration.
Generally, the earthquake induced tsunami waves will affected wet areas. So maybe the area in in Taiwan Island is not very large. Or
Yeah.
I mean, maybe a big earthquake or strong earthquake in especially, the tsunami maybe will affect very large area or very wide.
Yeah.
So your research area is not included in the.
I think the small islands is included in the tsunami affected area. However, as the historical records in
No,
around about
no historical record.
Yeah.
Yes.
Around 100 years, there's only one event about the tsunami that hit Taiwan and it caused damage That is about
Okay.
100 years ago in Keelung. That is in the main island in the north corner of the Taiwan.
Okay. No record of history.
Yeah.
Okay.
Yeah.
Okay. Thank you.
Thank you.
Yeah, thank you
Yeah.
for a question. And any other questions from the audience?
Okay. Hi, my name is Andrew. I'm from NCKU. Thank you for your great presentation.
Yeah.
I have a question about the coastal protection in Taiwan, since you discussed about the risk assessment and coastal protection, but I noticed that in Taiwan, they mostly don't include the effect of climate change and the current risk assessment of coastal protection in Taiwan. Even the design of the seawalls right now not consider the climate change effect. And we know that the climate change, like sea level rise, will be impact significant to the future coastal protection in Taiwan. So I just wondering why it's not included, and if there's any challenge or anything that make the Taiwan not including the effect of climate change in the coastal protection. Thank you.
Okay. Firstly, the risk analysis is based on the legal framework. Every 5 years, we should examine the hazard and the resilient propagate in a very short time. Every 5 years, our law regulates to do this kind of things. And the climate change is a long-term scenario. And our coastal protection facility is designed based on the criteria is based on the 5 years return wait period. In here, we actually consider the climate scenario in predict the future hazard proneness to estimated kind of new risk maps, but it's not showing in this topic because we are the small islands cannot suffering the hard engineering. So we here to stress on the adaptation strategy. So here, because so that we are not showing the climate change scenario here, but actually we do in some other research. Yeah.
May I know which one scenario? Because there's plenty of scenario of the company.
The midterm, the midterm and the end of the century. It's based on IR6.
IR6. Okay.
As I recall, the water level will rise 0.5 meters. Is in the worst scenario we'll consider in the simulation.
Is there any bureau that specifically do the simulation, or it's just taking the general number in the global climate change?
The big scale, the world scale, 0.50 meters take the global literature, but we put in our simulation as a boundary to simulate nearshore change. That will be our boundary to simulate that.
I see. Okay, great. Thank you.
Thank you.
Thank you. Any other questions from the audience? If not, Professor Huang also leave his email on the presentation, and this presentation is also recorded. So if you have any question, you're welcome to contact Professor Huang later through the email. And so I think I will sum up here. And thank you, Professor Huang, for sharing with us his experience. And also thank you all the audience for your questions. And we have a great discussion. And okay, so I will end the online meeting here. And thank you for participating. And we'll see you next time.
Thank you. Bye-bye.
Thank you. Bye.